I see we've got our next presenter available from Aix-Marseille University, Mr. Paul Sopena Martinez, who is a postdoctorate at Marseille University. And welcome, Paul. Paul's going to be presenting on laser-induced forward transfer, talking about improved versatility for PE applications. And with no further delay, Paul, the floor is all yours.
Yeah, well, thank you, and thank you very much for the introduction and for the chance to give it to presenting to you this technique that will be somehow different to what we have seen so far. So with no further ado, what I will be presenting in this presentation is basically like a little brief introduction to printed electronics to motivate the use of lasers in precisely the laser-induced forward transfer, and we will see some cases where this technique compared to other ones in printed electronics can provide an alternative. So as you all know, well, printed electronics appeared some years ago as an alternative to produce more cost-effective substrates and circuits on flexible substrates for wearable electronics and using organic materials. And basically, in printed electronics, we can find two kinds of techniques. On the one hand, we have conventional ones such as rotogravure, screen printing, that allow us to print, well, basically at very high speeds with a very high throughput in a very cost-effective manner. However, when we think of small-scale production runs, customization or defect repair, since these are non-digital, this becomes substantially expensive. And this is why the second type of printing techniques appeared, which is consists of these direct write techniques, such as inkjet printing or aerosol jet printing. So we have the same benefits of the other techniques, but with the add-on that these are digital test techniques. So we can just print from a computer file in a direct manner. However, well, not everything is perfect, and in these direct techniques, since we're printing from an output nozzle, not all kinds of inks can be printed. So only those with low viscosity, small particle size, or low solid content can be printed. So here's where I want to present that maybe there's a technique that can offer the best of both worlds. On the one hand, we can print these very high solid content of screen printing and do that in a digital manner. And here is where laser-induced forward transfer or lift meets this criteria. And how do we achieve transfer using lift? Well, the working principle of lift is quite simple. We just have a donor substrate and a receiver substrate. A donor substrate that we will cover with a very thin layer of the ink that we want to transfer, just a few micrometers. And then by means of a laser pulse that we will focus on the donor film, we'll be able to absorb this radiation that will induce a cavitation bubble just expanding forward, producing a jet that reaches the receiver substrate, and finally we deposit a droplet. So in these images here, we can see this transfer process from, I just want to say that on top we have the donor substrate and on the bottom the receiver substrate, and we can see how as the laser is absorbed at just, well, at 0 microseconds, it creates this bubble just leading to this jet propelling forward and finally depositing these droplets. We can basically change the main laser parameters such as power, so we can print droplets with different sizes, but at the same time we can print droplets with a very high repeatability and very fine resolution with just a few micrometers. And then, well, just by overlapping them, we can print complex patterns, such as the ones you can see here. So now that we've seen how lift works, and we've seen that we have no output nozzle, let's see how we can print these inks that cannot be printed otherwise with other direct write printing techniques. And for that, we will focus first on the lift of silver nanowire inks for producing transparent electrodes. So we all know that transparent electrodes are those materials that are both conductive and transparent to the light, and we can find them in touch screens, solar panels, or organic LEDs. And basically, what we typically use